Hi, I'm Chad Lawson. This is the Internet Radio Part 2, and you're watching Verbose Mode. This is Verbose Mode, the show dedicated to learning to learn and the freedom to fail. I'm Chad Lawson. Today we're going to talk about the Internet Radio Part 2. In our last episode, we talked about the project as far as what it was, how it came to be, and the fact that it has been the bane of my existence for the last couple of years. As we're now on these final home stretches working on getting toward the final project, I'm breaking apart each of the individual decisions. Today we're specifically going to be talking about the user interface. Now, when I started with this project, the actual components I had were pretty straightforward. The radio itself had these nice little knobs, plain and simple, and there was this front panel that would indicate with the little red line as to what channel you were on. So when I had the ability to start changing all this out, I had to make decisions on how I was going to, what I was going to have for those knobs, as well as then how was I going to display what channel I was on when I was using it. Now the first part you would think would be, this all sounds pretty straightforward. Let's start by talking about the input knobs. So one was going to be for volume and potentially on-off. You think about most radios, when you first click that knob to turn it on, you're going from an off state and ramping up the volume. And then on the other side, you're turning the dial, and in the case of this tube radio, you're actually pulling with that cord a mechanism over, as well as then turning the dial, literally turning the dial inside it to tune the radio channel. So what I wanted to do was figure out what was I going to do for those inputs. I had two different ideas in mind. One was to use a potentiometer, which is essentially a variable resistor. The nice thing about a potentiometer in terms of a Arduino or a Raspberry Pi is it's analog data that can be read in a wide range let's just say it that way. In most cases, like with an Arduino, I can read its input using one of the analog inputs from 0 to 1023, 1024 positions, 1 byte worth of positions. Obviously, I'm not going to have that many stations on here, but Arduino has a nice simple function to map. And if I say from 0 to 1024 should go down from 0 to 6, then as I turn it, as it's going through it, it's automatically making the division and going through there. I have the same type of capability with a Raspberry Pi. I can take that input, and as the potentiometer increases in the amount of resistance it's providing, I can then read that and map it to my positions on my dial. Now I have these 7 positions here on my dial. They are all nicely spaced out. So okay, no big deal. But then the question was, at the time, I hadn't found a potentiometer that also had an on-off functionality, so that you would click it and it would go to on, and then as you dialed it up, that would provide the volume. So I looked at a lot of different options, and I also found what's called a Rotary Encoder. This was at the time, a new item for me. I've since played with them a little bit more. I'm going to go to the overhead, I think. So here's a Rotary Encoder with a little breakout board attached to it. So it's got the little pins for me. Now this one, in addition to being able to turn, and it's free turning, I can turn this all day long. I could do this forever, but nobody would watch me that long. But this also has a nice little click and a nice long stem to be able to get through all of this. So that's great. The reason I chose this partly is because of the little pins, the little breakout board. A rotary encoder is very different than a potentiometer. This is, as I mentioned, free spinning. I can turn this all day long. But what I get, there's essentially 2 pins for the data. One telling me I can read 2 individual clock pulses, telling me how far I'm turning it and in which direction. So as I turn it to the left, the top one, well, I should probably get it. All right, I'm gonna, let's see, let's come back from when I came from here. Came from here, I was showing this off. So the reason I selected to go with this particular rotary encoder is partly because it had these pins, it had the breakout board. Now, with the rotary encoder, as I mentioned, this just spins all day long. There was no limit to how far it will turn. So then, how does one determine what position you're in? It turns out you don't, at least not from a hardware standpoint. With a rotary encoder, there's two different clock pulses. One will help you determine the direction you're turning it, and the other how far. So by reading those two different pulses, I can determine, did I just turn it up or down, and how many times have I turned it while in that direction. And I can put a link to a article to show you more about how a rotary encoder works. But my reason for choosing the rotary encoder was I didn't want to limit myself. I didn't want to have the dial physically stop. I wanted to be able to keep turning. Even now as I'm wrapping things up, now that I'm talking about it with you, I'm wondering whether or not it wouldn't be better to find a nice good panel mount potentiometer and then be able to limit that. Because one of the challenges that I've also had while working with the software for this is that the rotary encoders and the timing that's required for them is pretty tricky. I only found one decent library, and there will be a link in the show notes to the library that I'm currently using for the rotary encoder that provides that kind of real-time clock to be able to measure those pulses on a Raspberry Pi. On an Arduino, this is pretty dead simple. But that was one of my challenges when I started using a Raspberry Pi with a rotary encoder, was having that level of precision that I needed. As you'll see, and this is going to be on my fault, when we take a look at the code in a future episode, you will see that I probably need to put some more debouncing in there to be able to determine how many of those milliseconds have I gone in between turns to be able to keep it from just pulsing. But I still have a little bit of glitches I need to work out. But as far as for the rotary encoder versus potentiometer, I liked the fact that, the other reason for it was, at the time I didn't know of any panel mount potentiometer that had an off position. Everything just dialed from 0 to 100, and I didn't like the idea of leaving it on all the time. I mean, I could, I guess, read once it got all the way down to 0 on the volume, read that as an off, but I loved, if I was going to do that, I wanted some sort of tactile click to let you know it was going off. And since I didn't have a panel mount potentiometer that could do that, the nice little click pushing on this was going to be able to provide it. So the difference, I could have chosen the potentiometer, and as of this particular episode, I still might. But my library I'm dealing with right now is the rotary encoder. So I needed two different channels for that, and then I also needed a way to display what channel I'm on. Now that I've got a way to read that, the software can go ahead and pick up what's going on with the rotary encoder. One rotary encoder determines volume from 0 to 100%. The other one determines the channel. And again, I've got 7 positions on the dial. As you can see in my software, I accounted for the idea of I didn't want to have to keep changing my code every time I went beyond 7. So if I wanted to go to channel 8, I didn't want to have to rewrite the code to then divide up my position between there. So you'll see that my code has a point where it hits that 8th position and then changes color of the lights. Now that brings me to my next point. How was I going to display on this dial? Originally, I was thinking about just having individual LEDs and just going with a nice red LED to be that position. And I thought about lining up 13 or 14 LEDs in really tight position and being able to, as I turn the dial, kind of fade one into the next, into the next, into the next, to be able to show where I am on the dial. But I also thought it might be fun to play around with something called a Neopixel, which is it's a WS2811 LED or a WS2812, and It's a particular board, and I'm going to try going to the overhead. These individual little discs, the Neopixel is, I've only seen the term Neopixel specifically by Adafruit. The rest of the world seems to call them 2811s, 2812s, WS2812s. But what it is it's an RGB LED that has on the, whatever form factor it is, this just happens to be one form factor, it has power in, ground, so it has power and ground, and then it has a data in and a data out. And the idea is that in addition to being an RGB LED in a fairly small form factor, it also has something similar, if not exactly like a built-in shift register. So as you're pushing those little ones and zeros in to represent how much red, how much green, how much blue, once you have filled up one pixel, it then pushes it onto the next one and to the next one. The upshot of this being that I can control a near infinite number of NeoPixels with one data line. As long as I have enough power, and that's a challenge in some of my other projects, is how much power can I get out to power all these pixels. But as long as I have enough power and I can ground them, the only limit I have is how much memory do I have. On a Arduino, that might not get me all of the ones I want. I might have to go up to a larger Arduino factor. But on the Raspberry Pi, I have plenty of room to maneuver with. So I immediately began the process of playing around with my Rotary Encoders and my pixels. And I spent the better part of a night, let's see if I can get this in here exactly where I want it, making this. So this is, I've got precise, I measured out using a nice small caliper, measured out my exact distance in between to match up with my positions on my plate. I measured this all out and determined how far I needed to go, and I cut these exact wires and I soldered them on. This was a very time-consuming, tedious process because I wanted to get this right, and I wanted to have this be exactly where it's going to be. This was going to be a very big project for me. And I got this working, and I connected it up through some jumper wires to a Raspberry Pi. I fired up some demo software, had the lights going beautifully. Everything was working great. I'm still a little bit, even though I'm not using this in the final project, I'm still really proud of the work that went into this. Now, no sooner did I make this and was showing this off at the makerspace than one of my friends, Chris, asked why I didn't make my own custom board. The answer to that was simple. I have no idea how to make a custom board. I'd never made a custom printed circuit board. I'd never even had an idea of how to do that. So Chris sat down with me and worked on the idea of making my own circuit board. So there's a company called Oshpark. Let's go to the close-up. And I'm going to actually go to the overhead because I think I'll be able to get a slightly clearer shot of this. So we went through Eagle Software, and he helped me lay this out. It's got the 7 individual pixels. These are in surface mount form. There are small little capacitors underneath each one. Over here I have my input, and then there's a fairly large capacitor on the back. And the reason for that is to handle uneven fluctuations of power coming in so that I don't end up burning out a pixel, which I have managed to do in some projects where I was just trying to throw something together quickly, like a set of Christmas lights, and I didn't have a capacitor on there, and suddenly I've killed the first LED, the first pixel, and had to remove it. So this provides for that kind of stability. So then we took and sent this to a company I mentioned, Oshpark. They are known for their famous purple boards. The only downside I found to Oshpark is that you're required to get 3. And you can do multiples of 3, but your minimum order is 3 boards. I only needed 1. So you're paying by the square inch, but then you're getting 3 of them, which is fine. The first one trying to put it together didn't work exactly the way I wanted, so the second one came out much better. So I hooked this up to my software, same exact set up as I had with my individual little ones that I put together, and everything was still working great. So at this particular moment in the project, I have rotary encoders to handle input. I've got some good code that will allow me to read that. I ran the initial software that I mentioned before. I have all of this going just swimmingly, except for a problem. So the software that I'm using, actually any music software on the Raspberry Pi, needs to go out through if you're just using a Pi on its own, goes out through the only pulse width modulation pin on the Raspberry Pi. Pulse width modulation is what allows me to turn a light on and off very quickly so that it looks at a certain level of brightness. It's a very powerful tool, heavily used a lot in my work in Arduino, but there's only one pulse width on the Raspberry Pi. And pulse width is what I need to be able to send data to my pixels, and it's what I need to be able to drive my audio. So the very first time, and by the way, this is very early on in the project. I'm so incredibly proud of myself. I have a custom board. I've chosen this. I've got software installed. Everything is going beautifully. And I hooked this all up and I figure I am on the home stretch. And as the pixels start to light up and do their little show, the music is hearing this little doo-doo-doo-doo-doo-doo. Yeah, it's an annoying sound, and that's not even a good approximation of it. This little wobble over the top of it, and as the pixels pattern changed, so did the wobble. It turned out that's because the two of them were trying to drive the same pulse width modulation pin. So I did what any really good over-engineer would do. I come from a long line of over-engineers. My father makes Rube Goldberg devices look like the most basic things on earth, and I have inherited that gene. So I immediately started coming up with, well, if I've only got one pulse width modulation, what I could do is then drive the audio, because I wanted to keep the Pi clean. The very first thing somebody suggested to me, was, fine, use an external, like a USB sound card in the Pi. And I went ahead and got one, and it worked fine, but it just didn't fit what I thought this project should be. So I started down this long line of ways of using a Pi to interface with an Arduino, and then have the Arduino read the rotary encoders and send that information. Then the Arduino would send information down the line to the Raspberry Pi to control the Raspberry Pi. And then the Pi would send information back up to the Arduino to let it know what channel we were on, what volume, and then adjust the amount of lights. I spent a lot of time on this. I mean, a lot of time. I first tried just using, there were two different communication forums between the Arduino and the Pi that I considered. I2C or I2C, I'm not sure how you pronounce that, but it's integrated circuit communication. It's being able, and the beauty of it is that it only requires, besides power and ground, two wires, a clock pulse, and a data line to be able to communicate. And you can have many devices along this bus, each of which connects to the clock and to the data, and they can all communicate back and forth to each other, though there's usually one master device, in this case the Raspberry Pi. Everything was going to be beautiful. I'd have my Arduino, I'd have my Raspberry Pi, the two of them would talk over I2C. Wasn't going the way I wanted, and I was having a hard time really coming up with because now that I'm doing this, now I'm having to come up with my own format, my own protocol for these two devices to communicate with each other. And I spent a lot of time dealing with that. I will post a note I will post a link in the show notes to my GitHub for this particular project, and you can see just as my brain begins to unhinge at this point, as I put in I2C code, I strip it out and put in serial code. Serial's got to be great, right? It's the stuff that I dealt with back in my BBS days of knowing how many data bits, how many parity bits. This is going to be perfect. I'll do serial communication. I can set the baud rate. Beautiful. Nope, drove myself insane, and you can see that in the code as well. Finally, I realized, talking to somebody, and might have been my wife, that I was really over engineering this. Why not take everything back to the Pi and just find another way to, instead of having to do the communication to a separate device, do it directly on the Pi, and let's just go ahead and use that USB sound card. Later, when I actually talk about that part of the hardware, the sound part of the hardware, you'll see that there are also additional options that, besides the USB sound card, that could also work using my same device. So what I ended up doing was taking a proto board for a Raspberry Pi. Let's go to the front. So this has the connector for the Raspberry Pi, and I have just taken some male headers and soldered them onto here, and then run wires to their individual little connectors. I'm going to switch to the overhead. So in this particular breakout board, across this row right here is all of the pins broken out from the Raspberry Pi. So I just had my connectors hooked up, and the two different rotary encoders are pretty similar. Here in the middle is my pixels, and there's only the one pin that can do the pulse width, as mentioned before, and everything has its power and ground. So I kept everything nice and color coded. So this then I can just attach to my Raspberry Pi, and then attach my various inputs using jumper wires directly to this, and then put this all on the front panel. So that's where I'm at this particular moment. I have this Lasercut front panel, and I intentionally distressed it using the sandblaster we have at the makerspace. So the display board mounts back here behind this, and then each of my rotary encoders through, and I will just have to attach my knobs once I get them into place. And I've got the beginning of a nice little interface. Everything's ready to go. There's two pieces of Lasercut here. Everything, as you can see, mounts nicely. So we're getting toward the end here of coming up with a stable version of this. As I mentioned, even just in the part of preparing for this particular episode, I started thinking about the idea of using panel mount potentiometers instead for the inputs, because I did find one in more recent history that has a nice satisfying click for an off position. But that, at this point, that has been, I think I mentioned this in the last episode, that has been the biggest challenge I've had with this project. I get to a certain point, personally, I get to a certain point within the given project, and I run into a stumbling block, and I kind of give up on it and go and try something else. I'm almost done using the rotary encoders and the pixel board that you see here. I'm just going to get this project finished and working, and then I'll go through and potentially do some additional changes. But hopefully that gives you an idea for this project of why I made those particular decisions of potentiometer versus rotary encoder, about using Neopixel as opposed to using, I only have so many pins that I can use for this, and I didn't want to over-engineer it. So if I was going to use 7 or even 13 LEDs for the display, individual LEDs, I was going to have to find a way through what's called either multiplexing or charlieplexing, where you are taking a grid of the power and the ground lines and controlling those pins to determine which within a grid, even if they're just lined up straight across, within a logical matrix of determining which LED comes on. And the more I read about that, the more I realized even then that I was going to be over-engineering this. The nice thing is with the Neopixels, I get that for free. I can just simply send my data down the line and everything as well. So we've got our inputs with our rotary encoders. We have our outputs with our Neopixels to be able to display what we're on, what the volume is, what the channel is. I'll start looking at code in a later episode. We'll see how I'm controlling back and forth between all the different pieces. And if you have any questions at this point, please remember to email at feedback@verbosemode.tv or on Twitter at Verbose Mode TV. Also, if you're liking the show, please stop by our Patreon page and give us a little bit of love and support. We have a few different projects that are goals that are set up now on the page to be able to do some better lighting, better video equipment, as well as upgrading the studio hardware and software. So stop by that. I will also have in the show notes a list of upcoming maker fairs around the world. This particular time of year, there's only a couple here in the States. One is actually relatively near us. But if you get a chance to, if you're in the area of one of the maker fairs coming up, please do yourself a favor and stop by the greatest show and tell on earth. Stop in and talk to the makers, and hopefully that will inspire you. Hopefully I've inspired you. I'll see you next time, and until then, try again, fail better.